Hello everyone, this is Mrs. Lindsay. This is our first day on graph theory, and it is from chapter 5 on Euler circuits. The first thing that I want to talk about is the textbook that you have for this course. It's actually made up of two different textbooks. So the very first part of it, the author of this is Tannenbaum. That's what this is from, chapter 5. Then about halfway through, you'll see a yellow piece of paper with a divider. And then the textbook switches, and I go by the authors there. There are three of them, and I'm just going to take the letters of their last name. So it's MHH. That would be the second half of the textbook. So please just pay attention to that. If we switch, again, this is the first half of the book. Author is Tannenbaum, and then there's a second half of the book, and there's three authors, Miller, Hornsby, and Heron, and I'll call that MHH. But again, this is from the first part. Okay? All right, so what is graph theory? Well, graph theory is really the geometry of location. So let's take a look at a problem that we have here. It is a problem from the 18th century. We have basically a town, it has 7 bridges, which crosses a river, and they connected 2 islands in the river with each other and opposite banks. Okay. So, question is it possible to cross the 7 bridges in a continuous walk without recrossing any of them? So this is kind of a famous problem, and it was solved by Euler in 1735. And we'll actually figure out the answer to this question as we move along through the notes. Okay, so what did Euler do to solve this problem? Euler represented the land masses by points, which he called vertices, and bridges by line segments, which he called edges. The result of this is what we call graph theory. That's a new branch of mathematics. Okay, it was widely developed in the 20th century. Why is this important? It really helps us in terms of transportation networks, communication, scheduling, routing problems. I'm going to show you a couple of those. Computer science is another huge portion of that. Again, routing is really, really important in a lot of our daily activities. Okay, so I would like you to pause the video right now. There are 3 examples on page 140 in the textbook. And again, this is in the first part of the book. You'll see that there's an example. It's only a paragraph of 2 for each of these: security guard, mail carrier, and UPS driver. I'd like you to pause, read those, and think about what are the differences between these problems. Okay, so hopefully you read through those. And the security guard versus the mail carrier versus the UPS driver. So the security guard, and we're not necessarily going to answer these routes. We're just going to talk about the differences of them. The security guard wanted to cover everything. Okay, so they wanted to go down every single street. These are all the exact same neighborhood. Wanted to go down every single street, and they wanted to start and stop at the same point. And they wanted to be efficient. So in other words, they really didn't want to repeat any of the streets if they didn't have to. This is probably something we're going to call a circuit. Okay. Okay, so let's talk about the mail carrier. Oops, apologize. Going the wrong way there. I'm going to do this. Okay, the mail carrier. All right. So, exact same thing. Wanted to go down every single street. However, each street would probably have 2 passes. So there are now repeats. Because you got to get one side of the street versus the other side of the street. All right. So now let's talk about the UPS driver. All right, the UPS driver didn't need to go down all streets. They just need to go where the packages were delivered. So these paths or these routes would be different. What's efficient for the security guard would not be efficient for the mail carrier or the UPS driver. So they all would be different. Okay. All right, so let's talk about graphs. A graph is a finite collection of points and collected line segments. Points are called vertices. The line segments are edges. Again, that's what Euler made that bridge problem out of, right? Made points and line segments, vertices and edges. Okay, so these line segments, we don't have, we could have some curves in there. Okay, and we don't really talk about direction. You'll see we have direction in here, but if I say AB or BA, not necessarily a big difference there. Okay, we will again kind of talk about direction as we go through these routes, but the edges, we don't really refer to those. Okay, so let's talk about a few different things here and point out some of these in terms of the direction. Okay, so connect the dots. In this figure, we have 6 vertices, A, B, C, D, E, F. Okay, each edge can be described by listing in any order the pair of vertices that are connected. Okay, thus the edges of this graph are listed in random order right down here is what I'm referring to. Of course, from my pen, and I don't necessarily realize it. AB, BC, CD, AD, DE, EB, CD, and BD. Now I wanted to point out a couple things. Notice CD is repeated twice here. This is what we call a double edge. So CD is what we call a double edge. And it's sort of this oval type shape here, but going back both directions. Could also be multiple edge. And then we also have BB, which is rather unique. BB up here, that is what we call a loop. Okay. So a little bit of definitions there and pointing out differences between edges and vertices there. All right, again, a little bit more with terminology here. Adjacent. 2 edges are adjacent if they share a common vertex. And the other one is 2 vertices are adjacent if there is an edge between them. Okay, so let's kind of take a look at an example of that. Here we have a graph. Vertices A and B. So A and B. So here's A, here's B. Since we have an edge joining them, they are adjacent. C and D do not have an edge, so they are not adjacent. Here we have, there's loop EE, right? And again, BC is what we would call a double edge or multiple edges. Okay. But because EE, this loop here, vertex E is adjacent to itself. So again, just example of those. Right, so let's take a look here. Oops, apologize. So we have another example. Edges AB and BF are adjacent, so AB and BF are adjacent. Same exact diagram as what we were doing before. And then on the other hand, we have AB and DE are not adjacent. Okay, they don't share a vertex like AB and BF do. So a couple things that I want to write down here as well. We have what we call the vertex set. That would literally just be the list of all these vertices here. And I'm writing it in set notation. Okay, and then I'm going to also write the vertex list. Sorry, it just keeps going back and forth on me a little bit. The vertex, sorry, the edge. And set notation, so I'm going to just start with A. So it goes A, B, A, C, A. Now I'm going to go to B. I don't need to repeat BA, I already have AB, so I have BC. However, I do need to include, since we have a multiple edge here, I need to include that twice. So I could say CB if I'd like, or I could say BC, BC. I do have to include that where I would not do AB and BA. I would not do that twice. So hopefully that makes sense because this is your multiple edge there. But otherwise, I'm going to continue with vertex B, so I have BF, BE, and then I'm going to move on to C. I'm pretty much so covered because I have CA and CB. Then I'll go down to D, DE, again because I already have DA, so I have DE. Then EE, because that's our loop. Then we have FH, and the last one should be FG. Okay. All right, some more terminology. The degree of a vertex, V, is the number of edges for which V is the endpoint. So in other words, in this case too, a loop would count as twice. Okay, and we'll go through an example of this. A vertex with odd degree is called an odd vertex, and a vertex with an even degree is called an even vertex. So here's the exact same graph that we've been doing on the last couple of examples. The degree of A, so this case right here, when I'm looking at A, I have 1, 2, 3. So I usually write a 3 here, but I went ahead and wrote it out for you, typed it, would be degree 3. So that would be an odd vertex. And you can see B would be 1, 2, 3, 4, 5, because this is a multiple edge. And the only one that's probably a little bit different is E. Okay, so now I'm looking over here at E. So not only do I have 1, 2, 3, 4. A loop counts twice. Okay, so that's the important part with that one. All right, more terminology. Path is a sequence of edges such that consecutive pairs of edges are adjacent and no edge is repeated. No edge is repeated. So the starting and ending point. So unlike the security guard who parks his car, he does not need to get back at his car. A path is usually denoted as a sequence of vertices. All right, so what's the difference between a path and a circuit? A circuit is a path with the initial vertex and the terminal vertex being the same. So the starting and ending point are the exact same. That is the difference between a path and a circuit. All right. More terminology. A graph is connected if every pair of vertices is joined by a path. Let me repeat that. A graph is connected if every pair of vertices is joined by a path. And we'll kind of talk about that a little bit more in our picture, our example coming up. A bridge is the edge that, if it's removed, causes it to be disconnected. So again, let's take a look at our same graph that we've been going over here. In this graph, we have a path. Starting at A, all right, starting here at A. Then we go to B. Then we go to E. Then we go to D. And that's a path from A to D. So we started here and we ended here. Okay. But ABC, BAD is not a path because edge AB is traveled twice. Okay. So let me erase what I have up here. Again, acting odd on me. So let me just erase this guy. Okay. All right. So again, AB, so A to B to C to B and then back to A. So again, here's where I cross. It's not a path because again, AB is traveled twice. That is super important to know there. Okay. That's why it can't be a path. Now we have a circuit. Starting here with, choose a different color. Now we're starting here at E, and we're going to D, to A, to C, to B, back to E. So we started and stopped here. So started at E, stopped at E. That is a circuit. Now, why is that at length 5? We'll count these. 1, 2, 3, 4, 5. That's the steps that we went there. Okay, it is connected. Okay, however, we do have bridges. Why we have bridges? Well, let's take a look here. So here I have FG, this one, and FH. If I take those away, if I take away FG, for example, G is just hanging out there. It does not connect. There's no other edge that G connects with. Same idea with FH. I'm actually going to add another one to this list. I would also add BF there as a bridge. Okay, because again, if I remove BF, now nothing connects B to any, or F to any of these points over here really at all. So I would connect those, include that as a bridge as well. All right, let's go back to our original problem in the very beginning of our notes here. All right, so the original question, if you guys recall, was, is it possible to cross the 7 bridges in a continuous walk without recrossing any of those? Okay, so you can see now what I did in this one is kind of mapped it out using edges and vertices. Let's take a look at it. Okay, so if we take a look here, if we start, let's just say, let's start at A. Let's just try something. Okay, so let's start here. And let's say we start, and we go up here. I'm going to kind of number the order I'm going. Up to R. Then I'm going to go back to D. Or not back to, so I haven't gone to D yet. And then I'm going to go to A. And then I'm going to go back down here to, I'm going to go back to L. Then I'm going to go to D. Well, I get stuck here. Even if I choose not to go to L, if I would have gone back to A, which I could do because, again, we have a multiple edge here, then I go to R, I can't get back to D. I miss this edge here. I got to get this edge. So what the problem is, I now have to go back, and then I could do, so this would be 6, 7. Then I could get back here, and I'm still not, I'm ending at a point that's not where I started at. So that's not going to be a circuit. Okay, so let's take a look here. Let's see why this is occurring here. Let's see if we can see some sort of patterns, and you'll see why this is showing up in just a little bit. All right, so how many edges do I have coming out of here? I have 3. How many do I have here? 1, 2, 3. A, I have 1, 2, 3, 4, 5. And at R, I have 1, 2, 3. So these are all odd vertices. Because they're all odd vertices, there are no Euler circuits or paths. So it can't happen. That is not possible to not retrace your steps at somewhere along the line here. Okay. So again, is it possible to find a path that travels each edge of the graph exactly once? No. Is it possible to find a circuit that travels each one? So again, both of these should be no. All right, so again, let's talk about paths and circuits. An Euler path is a path that travels along every edge of the graph exactly once. An Euler circuit is a circuit that travels along every edge of the graph exactly once. So there's no repeats with these. So a path has, again, 2 different points. One where you start, one where you end. But again, with it being an Euler path, and you can only go over everything exactly once. No repeats. Circuit has the same starting and ending point. But again, when you add the word Euler in there, that means, again, no repeats. Okay. So Euler realized that if there is an Euler circuit, that each time we enter a vertex, there must also be an unused edge exiting. Okay. That's why every single vertex, this is an important little part here, every vertex must be even. If you have every vertex even, there is an Euler circuit that exists. In theorem, graph G has an Euler circuit if and only if these 2 conditions hold. What we just talked about, every vertex has an even degree, and the graph has to be connected. Obviously, I have a disconnected. Note, If there is even one vertex of odd degree, there cannot be an Euler circuit. They all have to have even degrees. Okay? So the original problem that we talked about requires that we have an Euler path. Okay. Right, so we have, of course, an Euler's path theorem. Again, the graph is connected. The key to this one is markers that every vertex is even, but we have to have exactly 2 odd vertices, okay? And then it can be an Euler path. If the graph has more than 2 odd vertices, it cannot be an Euler path. I do want to note, a connected graph can't have both an Euler path and an Euler circuit. It can have one or the other. It cannot have both an Euler path and an Euler circuit. It can have one or another. So I'll write that down. I added something there at the end. Again, it can't have both an Euler circuit and an Euler path. It can have one or the other, but it cannot have, or it can have none. It doesn't have to, it's not required to have one or the other. Okay? So again, if we go back to our bridge problem, so here's our diagram. It is now easy to see why it's impossible, right, to retrace your steps of each of these, because we have 4 vertices. We kind of already talked about 4 vertices have an odd degree. That's why there's no Euler circuit. There's no Euler path for that problem. Okay, all of those are odd. So again, a little bit more information here. For small graphs, Euler circuits can be found by just using these following guidelines. Okay, so we're going to kind of come up with some rules and guidelines that will help us determine these paths and circuits. Always leave one edge available to get back to the starting vertex as the last step. So again, this is a circuit. The starting and the ending point are the same. Don't use an edge to go to a vertex unless there's another edge available to leave it, except for the last step. So again, if you have to go to a vertex, you got to be able to exit that vertex too. Let's take a look at a couple examples here. Let's look at the more simple graph on the left-hand side. Again, we don't have any loops or multiple edges, and there's not as many edges in the graph on the left. So you can start by actually trying to figure this out, like pick a starting point, maybe number 1, and try to either end at another vertex using all the edges or going back to 1. Or you can actually go through what are the guidelines to having an Euler circuit or Euler path. If it's a circuit, again, every single vertex needs to be even. So if we start here, this is even. 1, 2, 3. That is not. Already, it's not a circuit. Not an Euler circuit. We can stop right away with that. But we can keep going to see if it's a path. Because a path has exactly 2 odd. Well, we have 1 odd. Here's an even. 1, 2, 3. Here's another one. Uh-oh. It's not either. Because we have 1, 2, 3 vertices that are odd. We only need 2. Okay? So we can go through that exact same approach with this graph on the right. Again, a little bit more complicated. Okay, so with this next one again, which is a little bit more detailed, pick a different color here. I'm going to go ahead and just start counting. All right, so I have an odd here. I have 1, 2, 3, 4 odd there as well. I'm sorry, even. 1, 2, 3, 4. So if circuit's already out from the very first beginning, and I'm going to just keep going through here and counting these. So far, we're still on track for path, Euler path. 1, 2, 3. And we're good. We have 1, exactly 2. So that would create an Euler path. Okay, so you're going to notice with some of these as we, go through, I'm going to erase this, but it might be helpful for you to actually start drawing these 2 or 3 different times. And it's okay. Like, I mean, you can erase things like I just did. Again, write it a couple times, whatever works for you with doing these. It's just, again, a little bit helpful. Or draw it bigger so you don't get confused in which direction you're going. But since this V sub O and V sub 7 had the odd degrees, I need to start and stop with one of those. Hopefully that makes sense, because every single time I go into a vertex, I have to be able to leave it, and I won't be able to do that at an odd vertex. So I'm going to just start here at the V7, and I'm going to just start picking a direction to go. So I'm going to go up here to V1, then I'm going to go to V2 for no particular reason. Then I can go down here to V6. And again, notice how I'm numbering these. This is the order that I'm going, and I am putting an arrow so I know which direction I've gone, what I've covered, what I haven't covered. Now I can go back to my starting point. So again, I'm entering, and when I exit, that's going to be really important, because now I cannot even go back to this one. So it can't be my ending point. Hopefully that makes sense. So now I'm going to go to my ending point, but I'm going to leave it, and I'm going to keep going. And now this is not necessarily the only route you can go. That's something very important. Sometimes they are complicated and there's really only one way you can go. Sometimes there's multiple ways. So if you want to even try this a different way than what I'm going, I know I'm just talking as I'm going along through this, but I'm just making sure I cover every edge. And that I get back to my ending point here. Okay, so we would call this length 14, basically because it took us 14 steps to do our Euler path. Okay, and again, please redraw them, erase, whatever you find easier to do to help you with these. All right, let's try these. Do they have an Euler circuit? Explain. I'd like you to pause the video, push play when you're done, and check your answers and see if you came up with the same ones that I did. All right, so hopefully you got yes for the first one on the left there. That's because all even degree vertices. And the one on the right is no. And why is that? Well, I'll just pick out the ones that kind of ruin it for us or make it an answer be no. There should only be only two odd vertices. Not 4. And I'm so sorry my writing isn't the best, and the writing on a computer doesn't help that. So I try to always say what I'm writing, and I apologize for that. But hopefully that you got the same answers for this. So yes on the left, and on the right, the answer there is no. Okay. So let's see if we can even come up with a little bit more tried and true way of coming up with how to find circuits. Okay, so for large graphs, so usually a common real world application, like if you're talking about mail and UPS, I mean, you're not just talking about a single neighborhood, you're talking about a big, huge region, okay? Obviously, we'd use a computer, okay? That's going to definitely help the process much, much faster. But we need a step-by-step procedure for that, usually called an algorithm. Okay? So we have something called Fleury's algorithm. Pick any vertex as the starting point. Mark your path as you move from vertex to vertex. Travel along any edges you wish, except do not travel along an edge that is a bridge. So again, remember a bridge, if you take it out, it makes the graph disconnected. Okay, so do not travel along an edge that is a bridge for the graph formed by the edges that have not yet been traveled. I know that gets a little bit wordy right there. And then continue until you return to your starting point, okay, or ending point. So this doesn't necessarily just work for circuits, okay? So again, this is Fleury's algorithm. Here we have an example of the algorithm, and we're going to do a path on this one. And you can go through and determine the vertices. It does make a path because we have exactly 2 odd vertices. Okay, so I'm going to start here at J. But before I continue, I'm going to show you my first couple steps. I'm going to do this. Here's 1, here's 2. It doesn't have to be the same as mine, but I'd like you to try this one. Okay, see if following this guideline here, right, marking your path as long as do not travel along an edge that is a bridge for the graph formed by the edges that have not yet been traveled. So see if that helps you at all as you go along through this. It just takes practice too. Okay, so pause the video, try this, and then come back and check your answers with mine. Okay, so I end up having length 21. And I ended at E. Okay, so I kind of weaved my way around here. 4, 5, 6, 7, up back to J, and then I went back to B, kind of weaved my way around, and then I came back over here and keep going. And sorry, this should have been 17. I put 2 18s, 17, 18, 19, 20, 21. And again, it doesn't have to be mine, but you can't have repeats. That's the biggest thing with an Euler path and an Euler circuit. No repeats. All right, so what is this useful for? Again, think about what we read in the very beginning. UPS, so postal routes, garbage collection, snow removal. Again, you're trying to minimize time, fuel, costs, trying to be most efficient as you're doing this so you don't have repeats. It gets a little bit different with garbage, mail, because you want to go down the street twice, getting both sides of the street, versus, again, something like snow removal. Wouldn't necessarily have to do that. Depends upon the plow. Actually, you might have to, if it's a, the street is 2-way or 1-way versus actually even having a 4-lane highway. So that all matters. Okay, so however, these tasks must be done whether the graph is an Euler circuit or not. If the Euler circuit does not exist, how can we travel each edge of the graph, repeating as few edges as possible? How can we determine exactly how many edges will have to be repeated? Okay, so in other words, if we're repeating there, we're either going to have loops. We might have to make duplicate edges, but again, you want to minimize those as best you can. So you want to Eulerizing the graph. Kind of hard to pronounce there. Okay, so how can we do that? So we're going to look at the sum of degrees theorem. Okay, so in order to answer these questions, what are we going to do? The sum of all the degrees of all the vertices in the graph equals twice the number of edges. And that's going to be an even number. A graph always have an even number of odd vertices, then the odd vertices come in. Okay. All right. So what happens? So the number of odd vertices is 0. Then we have a circuit, which we knew that, right? All evens. If there are 2 of them, then we have a path. Again, this is nothing new. We've talked about those first 2 things. If we have number of odd vertices is an even number, 4, 6, 8, 10, 12, blah, 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 then we don't have either. If we have the number of odd vertices are odd, 1, 3, 5, 7, 9, etc. Go back, double check, this is impossible. Okay? So, we want to locate all vertices of odd degree. Add edges by duplicating existing edges until all vertices have even degree. This is done by forming paths between pairs of odd vertices. So again, we're going to Eulerize this graph. So we're going to take a look at it, and we're going to first locate all the odd degrees. So that was A, B, C, and E. Everything else, D has 1, 2, 3, 4. That's even. All these have even ones, right? So these are the ones we need to focus on. A, B, C, and E. Okay, so we're only going to really focus on those because these are the ones that are going to get us to a place where we get stuck. Okay? So if we add paths between these, which I did with the red dotted lines there, then we can get back and forth between those, now making, for example, let's start with B, 1, 2, 3, 4, an even degree. Now we've made it so we can actually all have now even. Okay, I'm not going to focus on that too much, but that is how you would make something in a real life situation where you can minimize, again, how many streets you have to go back and forth on, how many repeats you would have. Okay, so this is the end of our notes for chapter 5. I want to point out a couple different things as you move along. There is required homework that's either due on Thursday or Friday. Those are the online Canvas problems. You will get 4 chances to do those by the due date, and the highest score will be taken. Okay. There are also extra problems that I will always assign. That will be in each of the weeks. If you look at week 1, you'll see chapter 5. You're going to see a little blurb about what chapter 5 is about. You're going to see online homework, and then you're going to see extra practice problems. Those are from the textbook. The answers, there are selected answers in the back of the book. Now realize, again, there's 2 sections, so there's 2 sections of answers. So the Tannenbaum, it's about halfway through. You'll see the answers, and then it goes to the other part, the other new book. And then there'll be answers in the very back of the book for that MAH portion. But again, there are answers. If you have any questions about those at all, please email me, ask me questions. I'm here to help. So again, Canvas problems are graded, 4 chances to do them. That'll be part of your actual grade. It takes your highest score. Extra practice problems in the textbook. Answers are in the book. Those are just to help you review, prepare if you need to go over any of those. Okay. The last thing that I'm going to leave you with is at the bottom of the homepage on Canvas. There are extra videos. I found some extra videos online. They are not me, but these videos will go through extra examples. So if you're looking for more Euler Circuit problems and you want to go through those, again, please check those out. Those are very helpful and very useful. Again, I'm here to help you. So if you ever need help, please, please, please email me. I'm happy to show you or go through or walk through anything that you need with those. Okay? But this ends our notes on chapter 5.